Hello students, this is Chris from after I finished recording the lecture in order to give you this comment. Before you begin watching this video lecture, I would like you to solve as much of this document as you can on your own. And then come and watch this lecture if you want to see how I did it, which may not be how you did it. Great, that's all I have to say right now. Lecture begins now. Hello students. So, we've done a lot of things building the theory of logarithmic functions. What I want to do today is actually use what we know to do some algebra and to walk some examples that come from applications. So let's go ahead and get started. So let's start by just writing down all of the things that we know about logarithms. So one thing that we know about logarithms is the translation from log form to exponential form. So if you see an equation that looks like log base b of y, an equation in so-called log form, you can rewrite it in exponential form. When someone writes log base b of x is equal to y, you can immediately translate to x is equal to b to the y, which sometimes will put you in a better situation. One thing that you know about logs is the log base b of 1 is always 0, the log base b of b is always 1, the log base b of a product, log base b of x times y, is always the same as the log base b of x, plus the log base b of y. Logs turn division into subtraction. Log base b of x over y is the same as the log base b of x minus the log base b of y. The log base b of x to the y, whenever you see an exponent inside of a logarithm, you can pull it out front as a multiple. Log base b of x to the y is the same thing as log base b of x multiplied by y. The change of basis formula. If you see a log whose base you don't like, you can re-express that log in terms of a log whose base you do like. The log base a of x is the exact same as, for any base b you want, the log base b of x divided by log base b of a. There's an exponential change of basis formula. A to the x is the same thing as b to the x, well, almost the same as b to the x. It's b, the same as b to the x times the log base b of a. So there's some facts we know. Let's use these to achieve some things. So, let's start by solving equations. Let's try to solve this equation. Log base 3 of 3x plus 5 is equal to negative 1. So, the first thing you notice is this is an equation that is in log form, and all of the x's are inside of the parentheses in the logarithm. That means that if I rewrite it in exponential form, maybe I'll, get something better. If I rewrite it in exponential form, I'll get 3x plus 5 is equal to 3 to the power negative 1. You could rewrite that 3 to the negative 1 as 1/3. In fact, you know, why not? I will. That is now a linear equation. I know how to solve linear equations. I just need to subtract 5 over to the other side, and then divide by 3. So, doing that, I'll go ahead and spread myself out horizontally. 3x plus 5, I'll subtract 5 to the other side. That'll give me 3x is equal to 1/3 minus 5. And at the end of the day, I'm going to want a single fraction. So let's rewrite what we have there as a single fraction. How do you do that? Well, you need to get a common denominator. That's 1 over 3 minus, take 5 and multiply and divide it by 3 to get a common denominator of 3. 5 times 3 is 15 over 3. Now it's easy to do the subtraction. That's negative 14 in the numerator divided by 3. So that's maybe a long enough step that it's worth summarizing it. Right, that gives me 3x equals negative 14 over 3. And now what do I need to do to solve for x? I need to divide by 3. Give me x equals negative 14 divided by 9. There's the solution to this equation. Cool. So, let's just keep right on trucking. So let's take this next one. Suppose I want to solve the equality 2 times the log base 4 of x minus 2 is equal to the log base 4 of 2. Well, so in what we did last time, it was really useful to have all the logs on the same side, and we don't have that right now. So let's take all the logs, put them onto the same side. They're all log base 4, so that's good. And let's move the 2 to the other side. So if I do that, I'll wind up with 2 times the log base 4 of x plus 1, I'll leave that bit alone, minus the log base 4 of 2 equals 2. So far, so good. So the stuff on the left-hand side is now an expression that just has a bunch of log base 4s with some numbers in them and combined together algebraically. Maybe the first thing I'll do is I'll say, well, that's a multiple of a log, so I can take that 2 and move it into the exponent. That'll give me the log base 4 of x plus 1 squared, maybe just for the sake of being explicit. Those two 2's that are indicated in red are the same 2, minus the log base 4 of 2 equals 2. So now I see a log minus a log. A logarithm minus another logarithm is the quotient, the logarithm of the quotient. So this will give me the log base 4 of x plus 1 quantity squared divided by 2. Where in this case, the same thing for emphasis, this 2 is the same as that 2. Nice. So now, this is an equation in log form. I can rewrite it in exponential form. Let's do that. Rewriting that in exponential form will give me, so if you like, I'm going to rewrite this log form equation in exponential form. That'll give me x plus 1 quantity squared divided by 2 is equal to 4 to the power 2, also known as 16. Nice. So let's carry on. This is now a polynomial equation. Polynomial equations aren't so hard to solve. So the autopilot way to do this would be to try to write this as something of the form ax squared plus bx plus c is equal to 0 and use the quadratic formula. But I'll go ahead and say I'm not a machine. I can be a little bit more clever than that. The only place where I see an x is inside of this expression that has a square in it. So I'll just get that on its own, and I'll take the square root. So to do that, I guess I need to move the 2 to the other side. That'll give me x plus 1 squared equals 2 multiplied by 16. And on the one hand, 2 times 16 is 32, but I won't use that. 16 is already a perfect square, so simplifying this any further would actually make the next step more difficult. That's not saying that you can't, just I won't. So now I need to take the square root of both sides. That'll give me x plus 1 equal to plus or minus the square root of 2 multiplied by 16. And now you see why I left that 16 alone. Do you see any perfect squares under that square root? Of course you do. You see the 16, and they're multiplied, so that means you can pull the 16 out. So I'll get x plus 1 is equal to plus or minus, square root of 16 is 4, times the square root of 2. So I'll get x equal to negative 1 plus or minus 4 square root 2. And there's the bit of concern you should always take. The bit of concern is this actually in the domain of consideration? Well, let's find out. So the only place in the original expression that I see an x inside of the parentheses is right there. That looks ugly. Is right here. So let's check the domain by using that. So for this, the original expression, this, to make sense, I need x minus 1 to be bigger than 0, so x needs to be bigger than minus 1. Oh, well, but look at this. I see here two different types of numbers. One of them is -1 plus a positive, and -1 minus a positive. -1 minus a number is going to be less than -1. Only x equal to -1 plus 4 times the square root of 2 is in the domain. Everyone feel pretty okay? Good. Let's keep right on going. So I know that I just went through 2 of these. And I really encourage you to have done all of these already, maybe even checked your answers by plugging them back in using a machine to help you before you watch any of this lecture. I'll add something at the beginning saying that. But let's keep on going. So let's try to solve this equation. 2 times the natural log of x plus 1 minus the natural log of x plus 2 is equal to 2. So maybe I'll take this mindset. I'll want to move all of the logs to the same side so that I can rewrite this thing in exponential form when I'm done. So let's do that. So I think I'll do 2 moves at the same time. So first I'll use the fact that I see a 2 in front of a log to transform this first bit into ln of x plus 1 quantity squared. And those 2 2's are like the same 2. Minus ln of x plus 2. I'll just leave that alone. I see an ln of 2 on the opposite side of the equation, so let's just subtract it over. Minus ln of 2. Just for emphasis, that's that ln of 2. And I've subtracted ln of 2 from the other side, so that side is equal to 0. Oh, nice. So now I see a log minus a log minus a log. Log turns subtraction into division. So this will leave me with ln, big parenthesis, x plus 1 quantity squared divided by 2 times x plus 2 equals 0. That is now an equation in log form, so I can rewrite it in exponential form. Doing that, I see x plus 1 squared divided by 2 times x plus 2 equals e to the 0. Right, because ln is log base e. Oh, but e to the 0, that's 1. So that's an improvement. And that's now an algebraic equation. It's just a rational equation. I can solve rational equations by clearing the denominator. Let's go ahead and do that. So let's see, if I take that and I clear the thing circled in red and clear the denominator, I'll get x, well, let's even FOIL out that x plus 1 squared, x squared plus 2x plus 1. So this thing in the numerator is exactly that. And I'll multiply the denominator over to the other side. parentheses matter. Nice. So this looks like it's going to be an easy equation to solve. X squared plus 1, x squared plus 2x plus 1 is equal to, distribute out the right hand side, 2x plus 4. Let's subtract 2x from both sides. That'll have the effect of killing off both of these. Then I'll subtract 1 from both sides, leaving you with x squared equals 3. So x equals plus or minus square root of 3. And, well, now we have to play the same game where we ask if this is actually in the domain of consideration, and I just shifted to the left so that I could highlight all of the ingredients. So in order for this log to be defined, x plus 1 needs to be bigger than 0. So x needs to be bigger than negative 1. X plus 2 needs to be positive, so x needs to be bigger than negative 2. Between these two, this condition is strictly stronger. Whenever x is bigger than negative 1, it's also bigger than negative 2. So I just need to check that. Is this number bigger than negative 1? Well, let's see. The positive branch definitely is. So x equal to positive root 3 is a solution. But negative root 3, not so much. Negative the square root of 3 is negative 1 point something. So negative square root of 3 is not in the domain. So x equals plus square root of 3 is the only solution. Cool. Carrying on. So, right, if this were an in-person class, I would spend a significant chunk of time just saying, I'm going to be quiet, you're going to solve this next equation, but I don't really have that option. So I'm going to go through the lot of them. You might watch it at 2x speed or something, or skip through some of these examples altogether. Let's solve this next equation. 2 times the log base 3 of x plus 1 minus the log base 3 of x plus 2 is equal to 1. Alright, so I'm going to start combining some steps. I see that there's a 2 in front of this log, so I know that I can move it into this exponent. I also see that there's some subtraction. That subtraction will become division. So this will give me the log base 3 of x plus 1 squared, where this 2 is the 2 that's circled in gold, divided by x plus 2 equals 1. So I've just combined all the logs into a single log. This is now an equation in logarithmic form. I can rewrite it in exponential form. If I do that, I will get x plus 1 squared divided by x plus 2 is equal to 3 to the 1, which, fancy that, that's just 3. That's progress. Because now I have a rational equation. I see a rational function equals 3. So let's keep on going. A rational function equals 3. I'll move the denominator over to the other side and I'll FOIL out the numerator. X squared plus 2x plus 1 is equal to 3 multiplied by x plus 2. So I'll see x squared plus 2x plus 3 equals 3x plus 6. Alright, so this is a quadratic equation. Just move everything to the same side and see what happens. X squared minus x, because I'll subtract 3x to the other side. 2x minus 3x is minus x. I'll subtract the 6 to the other side. 3 minus 6 is minus 3. And maybe I'll do a quick check to see if this factors in any obvious way. So I would need two things that multiply together to be negative 3, but add together to be negative 1. So the only options are negative 3 and 1, but those add together to be negative 2. Or there's positive 3 and negative 1, but those add together to be positive 2. So this won't have any irrational solutions is what that check has just done. So the only thing we can do now is, well, I guess we could complete the square, or we could use the quadratic formula. I'll resort to the quadratic formula this time. It's nice to do these things in a variety of ways. Giving me x equal to negative b. B looks like it's negative 1, so negative 1 is positive 1, plus or minus the square root of b squared, negative 1 squared is 1, minus 4 times a, which is 1, times c, which is negative 3. All over 2 times a. Negative 4 times negative 3 becomes a positive. So 1 plus or minus 13 over 2. 1 plus or minus the square root of 13 over 2. And just like all the other ones, I see 2 solutions. Let's try to decide if they're valid solutions. So what are the constraints? This bit says x has to be bigger than negative 1. This bit says x has to be bigger than negative 2. So take the weakest of the two of them. X has to be bigger than negative 1. Excuse me. So I know that x has to be bigger than negative 1. And on the one hand, we could directly stare at this expression. Well, the plus 1 is, the one with the positive is obviously fine, right? Square root of 13 is bigger than 3. So 1 plus something that's bigger than 3 divided by 2, yeah, that's bigger than negative 1. In order to check if the negative branch is, there are lots of different ways to do it. You can do it by just thinking about how big the square root of 13 is. Use the fact that it's somewhere between 2 and 3 to meditate on what it should be. Somewhere between 3 and 4. Square root of 13 is somewhere between 3 and 4. Instead, I'll resort to you using a machine to help me do the computation, and you don't need to watch me type. I'll go ahead and pause. Alright, I'm back. It looks like 1 minus the square root of 13 is somewhere around negative 1.3. Which is not bigger than negative 1, so that's not in the domain. So x equals 1 plus square root of 13 over 2 is the only solution. Groovy. So I think what I'm going to do is I'll break this lecture here in order to have conveniently sized, easily digestible chunks. You should come back to this, come back to the next lecture, and we'll talk about solving exponential equations using these techniques.